Hello, welcome to the Institute of Biostatistics. This presentation is part of a series of lectures planned to be given on Bayesian analysis by the Institute of Biostatistics. Today, we are going to discuss about an illustration of the Bayesian analysis through R. This was promised last time on a previous video on Bayesian analysis. So the plan is to illustrate the case of regression in the context of Bayesian analysis. The data used are monthly weather data for 38 years. The regression considers the time series nature of the data. The Bayesian approach utilizes prior information available on the parameters and generates posterior means and credible intervals of the regression coefficients. So that said, we can straight away go to the R platform. So the first task for us is to load or import the data from external file, which is an Excel file, to the R environment. For that, we had to utilize a read Excel package, and the data is available in C drive, and we get the data into R. The data is on weather variables, many of them, and for a period of 38 years, 1983 to 2021, monthly averages. So there are 466 values. So for some manipulation on the data, we may require deploy R pack, and we select a subset of the data. We can have a view of the data here. We have selected rainfall, temperature, and relative humidity. These are standardized values, meaning by deducting mean and dividing by standard deviation, we have made them free of units. So let us first execute ordinary least squares. So using the LM function, here dependent variable is relative humidity, and the predictors are temperature and rainfall. And let us get the summary. The residual statistics is given, minimum, first quartile, median, third quartile, and maximum value, followed by the regression coefficients, the standard errors, the t value, and the p value. And by p value, regression coefficients for temperature and rainfall are highly significant. We also get residual standard error of 0.4082 with 463 degrees of freedom. Adjusted R square is 0.75. And the overall F statistic shows the model is relevant in the sense with a high p-value, significant p-value. So, but we know that we have a time series data, so the successive values could be correlated, and OLS cannot take care of that because it is based on the assumptions of a Gauss-Markov setup that variance covariance matrix is an identity matrix multiplied by sigma square, requiring equal variances and zero correlations. So we need to change our approach. For that, we are utilizing CAR package, to check on this assumption. by Durbin-Watson test. So we have found that the autocorrelation of lag1 is 0.48 and DW statistics is highly significant, that is near zero value. So we go for the alternative hypothesis that rho is not equal to zero. So the next one of the alternatives is to utilize generalized linear model, which can do iterative weighted least squares. So we are using GLM function, and it is possible to specify a possible distribution form for the errors. This model is kept the same, and we implement that. Here, more or less the same values for the regression coefficients. If you browse through the OLS values, the regression coefficients are significant. But instead of ANOVA, what we get is maximal likelihood estimates. So null deviance for the intercept-only model is 321. For including both the predictors, rainfall and temperature, residual variance has come down to 77. So in fact, utilizing these values, we can compute a pseudo R-square value, like 1 minus 77.146 divided by 321.74. That would come to around 0.78, a reasonable value. If required, we can also test for the significance of the difference using a likelihood ratio test. Now, null deviance and residual deviance, these are all, as good as residual variance. Anyway, the archaic information criteria is 492, but that is useful only while comparing different models. Okay. So next we go for Bayesian regression using ARM package. Here we are fitting the same model with the base GLM function under the assumption that the residuals follow Gaussian or normal distribution. And it is possible to specify some priors here, but in the absence of any other information, we may go to default values. Prior mean is set as 0 for the parameters, and similarly for default values for variance parameters also. Prior.df equals INF indicates that the residuals have a normal distribution. And we fit that model, get the summary. The results are similar to that of GLM. So, but let us see the performance of this model by generating the predicted values, p-scores, and also plotting against the actual value. Here we see that there is a curvature here in the pattern. Ideally, we should expect a linear relationship between the observed values and predicted values. Okay. So let us try to correct for that. And most probably a quadratic model would be better to describe the relation between rainfall and the temperature with humidity. So whether let us generate the square terms and cross product terms and run the same model with 5 variables now, fit a quadratic surface and get the summary. Here, instead of 2 predictors, we have 5 predictors now. Temperature, rainfall, square terms of these variables, and the cross product terms. All the coefficients are significant. Also, we have similar values for null deviance, but residual deviance has come down to 55 instead of around 70 earlier. So the model has a better explaining power. Now let us retry predicted values plot. So here that curvature is almost gone. So now it's more or less satisfactory. So a quadratic model is fitting better than the linear model. So far the Bayesian regression we have run based on some a priori values is only empirical. Now we must go for a more detailed Bayesian fitting. So for that we need an MCMC pack, and we utilize MCMC regress function. But ideally we should have taken all the 5 variables here, but that will take a lot of computing time, which I am avoiding. Just for illustration, we are still considering only 2 variables. So we can specify a burn-in period of 3000. That is, the first 3000 values generated during the MCMC process will be discarded. So additionally, 10,000 values will be generated on the posterior distribution with a thinning interval of 1, meaning we will admit only every other value. So one value in between will be removed. That is to avoid the correlation between successive values generated from the posterior distribution. Otherwise, there is going to be correlation. We could have a larger thinning interval, and both these are default parameters. Seed, it will take NA means it will take its own seed for the simulation, and it's possible here now to specify the prior values of regression coefficients and their variances. These are coming from the empirical based regression model. So we can try that and get the summary. Here, there is not much change in the regression coefficient, but the advantage is that through MCMC, we are getting posterior distribution, and we can set up the credible interval. So these are HPD, highest posterior density, for each of the parameters involved, including intercept. So meaning, say, temperature regression coefficient 2.5% and C 7.5%, 95% interval. So the true parameter or true regression coefficient of temperature could vary from minus 0.48 to minus 0.35 with a 95% confidence. So unlike fiducial intervals, credible interval has a different interpretation. We are proposing that the true regression coefficient has an unknown mean, but it is varying. It's a random value, random parameter, and we are proposing that the true parameter value could lie between these two limits with a 90% confidence. But whereas in the case of fiducial interval, the parameter is fixed and unknown. We are trying to estimate that from the samples. And every time say we are establishing 100 confidence interval. 95% of them are supposed to include the true parameter, which is constant. So this is a technical difference between fiducial interval and credible intervals. So these parameters are credible intervals are established for each of the parameters, including the variance parameter. So the final test is we could just plot the posterior distribution for each of these parameters. Now here, the first 3000 values are discarded. So it goes up to the next 10,000 values. These are the actual plots, actual values plotted for, say, intercept regression maximum, temperature regression coefficient, rainfall regression coefficient, and residual variance. Now, this is the corresponding graph, frequency distribution, and for each of these coefficients, and they are more or less bell-shaped and normal because of our prior assumption of Gaussian function for each of these parameters. So that's it. So my suggestion is that you have seen a simple illustration of the methods. So other than theoretical knowledge, you must know how to implement the Bayesian methods also. So I hope I have covered at least the basic techniques. My suggestion is for you to get familiarized with all these packages in R and try to try out these methods by yourself. Thank you for listening. Thank you very much.